All right, so our goal today is to talk about energy in simple harmonic motion. We're going to start by talking kind of specifically about a spring system, since that was what we've been dealing most with. So if we picture a situation that's very dynamically similar to what we did in our spring dynamics worksheet, you're going to take a block and it is going to come in contact with a spring. And what we're going to assume is that the block and the spring stay together. But that basically the block is not permanently attached, so that way it'll get released again. So essentially what happens here at the start is you have some amount of kinetic energy, which then when you come in contact with the spring, you're going to start compressing the spring. So you're going to get some potential energy. We're going to reach essentially a point where, because the spring force is acting in the opposite direction of the velocity, that it's going to slow down until it reaches a stop. All your energy is going to be elastic energy, and then it is going to, because the spring force is still to the left, it is going to start to move left. The spring is going to uncompress. So when it goes back to its original length, there's not going to be any elastic potential anymore, and you're going to get the same amount of kinetic energy out of it that you had before. It'll just be moving in the opposite direction. So while the block is in contact with the spring for that section of the motion, the block is in simple harmonic motion, even if it is not like physically permanently attached to the spring. So a lot of times what they'll do is they'll give you situations where, okay, in case A, the block touches the spring but does not attach. And then other cases, they'll look at, okay, well, what happens if now the block actually attaches and permanently attaches so that it just continues to oscillate? So we can look at those two same situations all in the same problem. So looking at this in a little bit more detail, we're going to make a bunch of assumptions. We're going to assume this is a frictionless surface, which means that there are no non-conservative forces, because the spring force is conservative, and that's really the only force that's acting here right now. And so the total amount of energy of our system is going to be dependent on the mass of the block and the initial speed of the block. And then at some point between when the block has just touched to before it gets to its maximum compression, you're going to have a combination of both kinetic and potential energy. Now, the ratio of kinetic and potential is going to depend where in this range that it is located. But you have to realize, if you're not at the equilibrium point and you're not at the point of maximum compression, or extension, if you're actually being stretched, then you're going to have both kinetic and potential energy at the same time. And that total amount of kinetic and potential has to add up to be whatever the kinetic was at the start. And then when you're at the point where you're at the maximum compression, all of your energy has been converted into potential. So you basically have your maximum compression distance that can be found at that point in time. The block is instantaneously at rest. And then over time, the block is going to be pushed away by the spring. And theoretically, if there were no resistive forces, then you would get the exact same energy out at you start. Now, this is important to realize that although this makes a lot of sense, it's not that much different than what you probably were thinking before. The way this turns up graphically is going to look different when we start looking at the oscillation portion of this. So when we look at the mass on the spring, essentially what we're going to see is we're going to see an oscillating pattern. So we're going back and we are taking a look at what we knew before. So this is just the position versus time graph. So we're not going to look at that exact same one that we had before, but now we're looking essentially at a portion of an oscillation. So we are going to start here at a maximum amplitude. We are going to go through the equilibrium position. We're going to go to a negative amplitude. We're going to go to the equilibrium position, and then we're going to end at the exact same position we started. So if we kind of think about what's going on here, if this is my equilibrium position XO, essentially I'm going to start over here at a positive amplitude, and it can oscillate over here to a negative amplitude, and it's going to go somewhere in between. Now, we know that the velocity graph is going to be out of phase with the position graph, because your maximum velocities, your velocity is 0 when your amplitude is at a maximum. So you can see that those maxes and mins occur at the 0 points, whereas your maximum velocities occur when your position are is at 0. So this is important because when we look at potential energy is 1/2 kx squared for an object on a spring. You can do this for a pendulum as well. And the process is going to be similar, but a little bit different because you'd have to do this in terms of kind of rotational kinetic energy as we go through. So it's a lot easier to talk about the math on the spring here initially, but you'll see some pendulums later. And then our kinetic energy is 1/2 mv squared. So they're both squared. So what that square means is that whenever my position is at a maximum or a minimum, that means that my elastic potential energy has to be at a maximum. So you can see here, let me clear some of this ink so it's easier to see. So you can see that these maxes and mins on that position graph occur here. They give you maxes on that elastic potential energy. So in one period, so this is T here. So you're going to end up with those maxes and mins for that position graph being maximums for the potential energy. Plus, when you look at that formula, the potential energy is squared. That means you could never go to a negative number. So the minimum potential energy is actually 0. So you notice for one complete oscillation of the position, the potential energy goes from a max to a min to a max to a min to a max. So it essentially goes through twice as many maximums in the same amount of time as the position graph does. Now the velocity graph is going to be similar. Anytime the velocity graph is at a minimum or a maximum because of the 1/2 mv squared, because that velocity is squared, those minimums become maximums. So you can see those two yellow points right there end up occurring here. And you end up with the maximums for the potential energy occurring, for the kinetic energy occurring where the potential energy is 0. So they're occurring in opposite locations. And then because of the square, you can never go negative. So your kinetic energy can only go to 0. So whenever you're looking at the energy graphs, these are actually going to be sine squared and cosine squared graphs rather than cosine and sine. So that's why they look a little different, because they're not actually pure sinusoidal. And then you just have to be careful to make sure you don't draw these like jagged V's. They are sinusoidal, so they do have to have curves. Okay, they do have to have curves when you go through. They're harder to draw. So you can get those potential and kinetic energy graphs from your position and velocity graphs. Looking at the equations, subbing in our position function. So when you sub in our position function, the position is a cosine of omega t. So you end up getting the a squared out in front. So you get 1/2 ka squared times cosine squared of omega t. So if you were to graph this, it would be a cosine squared graph. And notice that this 1/2 ka squared is your maximum potential energy. That's your potential energy at the maximum compression or extension, the amplitude. Your kinetic energy, if you sub in the velocity equation, kinematic equation, you get negative a omega sine of omega t. And when you square that, you end up with 1/2, oops, got all this in there, the 1/2 ma squared omega squared for that. So that is going to be your maximum kinetic energy. So your maximum kinetic energy is going to be 1/2 ma squared omega squared. And you can use that. And so once again, that's going to be a sine squared function. So you can also look at these as if they were bar charts. So what we have going on, we're looking at different positions. So we're looking initially over here at different positions. So this is our equilibrium position right here. So at our equilibrium position, our potential energy is 0 and your kinetic energy is at a maximum. And that represents essentially the total energy of the system. So now from there, we can't tell just which direction that it's moving. We'd have to know more information because of the square, that kinetic energy is the same whether it's going to the left or to the right. Now, let's assume that it's initially moving towards the right. Then if it's initially moving towards the right at this point, as it leaves that equilibrium position, then at this point in between, so when you're exactly in between the equilibrium position and the amplitude, so you mean you're halfway, your kinetic and your potential are not equal. Your halfway position is not equal energy. Your equal energy is actually going to occur over here at the 3/4 position. And that's due to those squares in those equations. So when you are at the midway point of the amplitude, you're going to get more kinetic energy and less potential energy. If you keep going to the right, you're going to lose and eventually have no kinetic energy, and then all of your energy will be potential. And then when you have, that's where you have your velocity is equal to 0. So since your acceleration is towards the left, you're going to end up keep moving to the left, and then you're going to come back, and you're going to be at this same energy position that you were here, but moving to the left. So you're going to be decreasing in potential and increasing in kinetic. When you pass the equilibrium position again, you're going to be at your maximum speed, but moving to the left. So you're going to be all kinetic. And then you're going to move past that position, and you're going to start to lose kinetic because you're moving to the left. Your acceleration is to the right, so you're going to be slowing down. So when you're at this negative 1/2 of the amplitude, you're going to be back to having 3/4 kinetic energy, and you're going to have 1/4 of your energy as potential. Once again, the midpoint where the point where kinetic and potential are equal is going to be actually over here at approximately 3/4 of the amplitude. And so that pattern is going to keep happening. So you're going to be moving to the left. But you're going to be slowing down, and eventually going to come over here where all of your speed is gone because all of your energy is now in the potential energy stored in the spring and the block. And then since your acceleration's to the right, you're going to start moving to the right, and then you're going to start gaining kinetic energy, and this is going to go back and forth kind of forever. The other way to kind of look at energy diagrams is they often do position energy versus position instead of energy versus time. So, and these graphs work for both oscillating spring mass systems and oscillating pendulums. So your pendulum graphs will look similar to this as well. So what happens is when you're at that negative amplitude or that positive amplitude, you're going to have your maximum potential energy. Now, if you start at one of those total maximum places, then all that represents your total energy. So that means none of your energy can go above or below that. And you can see here that the point where your kinetic and potential are equal is going to be over here at some position X. That is not the midpoint of the amplitude. So, and this is going to be a parabola, an open face parabola, because its U is 1/2 kx squared. Now, your potential energy is always easiest to find because it's just dependent on your position. Your velocity is going to do the opposite, because if your energy always has to add up to this total energy right here, then that gives you your maximum energy. So if I'm at this point, then my kinetic energy is 0. If I'm at some point over here, I'm gonna know my potential energy because I'll know my position. And then basically I just subtract my potential energy from my total energy to find how much kinetic energy I have. And when you do that, you can actually do that for all those different points, and you find that you get a downward facing parabola for the kinetic energy. And that's essentially because your total energy is going to be constant. So those always have to change in the opposite manner. So that there is your energy versus position graphs. So you have in analyzing graphs of simple harmonic motion, and you're going to have to do a lot of graphing of position, velocity, acceleration for different systems. Using, if you're given a velocity graph, you should be able to create a position graph, or given a velocity graph, you should be able to create a kinetic energy graph, and then also be able to see how those vary at different points in time. So there you have it. That's simple harmonic motion.